Hey everyone, welcome back to the Summer Pi series, and in this video we're going to train the generative adversarial network that we made previously. So here we have our discriminator and generator, and now we're going to start a new code block so we could start the training process. So we'll need the number of channels, of course. We're using 3 because we're using RGB images. We'll have the number of feature maps, which will stick to 64. The size of the latent vector z will set to 32. I don't know if there's any rule of thumb to choosing this number, but I found that this works in my research experience. And we'll set epochs to around 1500 maybe. It's a lot, but that's how many epochs it does take to generate the higher quality images that I had when I was first doing this project. So now let's create our networks. I'll call our discriminator D, and we'll take in the number of channels and the number of feature maps. And then we'll call the generator G, where we have the number of channels, the number of feature maps, and then we also need the latent vector Z. Okay. Now we need to create our optimizers, networks. So each network, of course, has to have their own optimizer. So we'll say doptim equals torch.optim.atom d.parameters learning rate equals 0.0002. We'll do the same thing for the generator. Okay, so now we have our networks and their respective optimizers. Our loss will be, say, criterion. We'll just stick to the binary cross entropy loss that we've been using. And then if torch.cuda.is available, we'll pass our networks onto the GPU. And with that part said, since we started a new code file, we'll have to make sure that our settings uses the GPU accelerator, so make sure to keep that in mind. We're using the same dataset that we used when we were trying to automatically detect the gravitational lenses, so we'll go ahead and pick that file from the GitHub. Okay, so now we're about to run the block, the new block that we just created, so let's hope that this works. Okay, so no problems here. Next, we'll have to create some functions that will help us create labels for our GAN approach. Remember, now we're working with real images or fake images, not lens galaxies or regular galaxies. So I have a function called onceTarget, which takes in the batch size, and this will provide the labels for the real images. Torch.once batch size 1. So all this does is create an array of ones in the torch format, so we could use it for comparison when we're trying to get the loss. So if cuda.is available, we're going to return the ones on the GPU. But if we're not using the GPU, we'll just return the ones regularly. And we'll do the same for zeros because we need zeros to define our fake samples. Again, all it's doing is creating a vector of labels filled with zeros, and then here it was filled with ones. So return zeros, and this should be zeros as well. Okay, so now we have the labels figured out. Now we need to create latent vectors for our z. So create latent z. We'll take in the batch size and the size of the latent vector. All we need to do is say n is torch.random numbers, batch size, the size of our latent vectors, and 1. All this is saying is give me a batch of this many vectors of this size. So again, if we're using the GPU, we'll say torch.cuda.is available. Sorry, I forgot to add these here. I don't know if it matters or if it would give an error, but let's just have those to be consistent. We'll return it on the GPU, but if we're not using the GPU, we'll just return it regularly. We are using the GPU, but this is just as a safe way to do it in case you forget to turn on your GPU. Next, we'll say define train discriminator. And this function will train the discriminator network, so we'll need the real training images, we'll need the fake training images, we'll need the discriminator itself, we'll need the optimizer for the discriminator, and we'll need the loss that we'll use to generate the errors. So of course, we'll start off by zeroing out our gradients for the de-optimizer, and then we'll say n equals real train dot size 0, and all n is defining the batch size. So when we're using 0 target and 1's target, that's how we get it. So we'll say predictions on the real image will be use the discriminator on the real training data, and then we'll also say labels real will be 1's target n. So that's why we needed n. It's as simple as that. We got the labels for the real data now. Next, we'll need to do it on the fake data as well. So we'll say d fake train labels fake equals 0's target n. Now we just need to generate our errors. So we'll say error real equals loss predictions on the real versus the labels for the real images. On the other hand, we have the error on the fake images, which will say loss on the predictions on the fake data versus the labels of the fake data. And then our total error will be error real plus error fake. Then all we need to do is backpropagate and then take a step on the discriminator optimizer. And then we'll return the error so we could refer to it during the training process. And that's it. To train our discriminator, we'll make some predictions on the real images, we'll generate the labels for the real images, we'll calculate the loss on the real images, and then we'll do the same for the fake data. Combine them together, backpropagate the losses, take a step. So the train generator will be pretty similar. We'll take in the fake training data, we'll take in the discriminator so we could see how it's performing if the generator is able to trick the discriminator. We'll take in the generator optimizer and the loss. We don't need to put in the generator here because we're taking in the fake data, which means that the generator will be producing these images outside of these functions. So to move forward with this, we'll zero out the gradients for the generator optimizer. We'll say n equals fake train dot size. And the reason we put zeros here is because if you remember, our batches come out like this. We'll maybe have 4 images of 3 channels, 64 by 64. So the number of images we have is 4, which is the 0th index. So that's why we were putting 0 there. Now what we want to do is we want to get the predictions on the fake data. And we'll say D, we'll use the discriminator on the fake training images. And then the labels here will be a little different. So I'll call it labels tricked. And it'll be 1's target n. Remember, when we're training the generator, we want the images to be so good that the discriminator thinks they're real, meaning it accidentally gives them a 1, and that's how you know the generator is doing its job correctly. So the error will be the loss on the predictions fake versus the labels that we hoped for, which is labels tricked. Then we'll backpropagate our errors, of course, and take a step for the generator. And then return the error so we can refer to it during the training process. Okay, great. We've defined our training function so we could train the discriminator and the generator respectively. We created the function so we could create latent vector z's and the respective labels for ones and zeros. So now we could start the training process.